Today we are going to learn about navigating bias variance in machine learning models. In this video, we will explore how to balance bias and variance, understand underfitting and overfitting, and learn techniques to optimize model performance. You'll gain skills in diagnosing and adjusting model complexity for better generalization.
Welcome to our exploration of bias and variance within machine learning models. These two components are critical in determining how well your model performs not only on your training data but also on unseen data. Bias refers to the error due to overly simplistic assumptions in the learning algorithm. High bias can cause an algorithm to miss the important relationship between features and target outputs, leading to underfitting. On the other hand, variance refers to the algorithm's sensitivity to small fluctuations in the training set. High variance can cause overfitting, where the model learns the noise in the training data as if it were a true pattern. Striking the right balance between bias and variance is crucial. Too much bias, and your model oversimplifies the data, missing out on beneficial patterns. Too much variance, and your model might perform exceptionally well on training data but fail to generalize to new data. Throughout this video, we'll unpack these concepts, explore how they relate to model complexity, and delve into practical strategies for achieving a harmonious balance.
In the world of machine learning, underfitting and overfitting are two sides of the same coin, representing the extremes of model performance. An underfitted model is one that is too simplistic, failing to capture the underlying trend of the data. This typically occurs when the model has high bias. Symptoms of underfitting include poor performance on both training and test datasets. Imagine trying to draw a straight line through a curved pattern. Many data points are missed. Conversely, overfitting occurs when a model becomes too complex, capturing noise along with the signal in the data. This is characterized by high variance, where the model performs exceptionally well on training data but poorly on unseen data. Visual examples can help crystallize these concepts. An underfitted model might be a straight line through a sinusoidal pattern, while an overfitted model might zigzag excessively through individual data points. The key to effective modeling is finding the sweet spot where your model captures the essential patterns without getting lost in the noise. This balance leads to a model that generalizes well to new data, performing robustly in a variety of scenarios. Model complexity is a central factor in the bias-variance trade-off. Complexity refers to the capacity of the model to capture intricate patterns in the data. More complex models, such as deep neural networks with multiple layers, have the potential to fit complex patterns and reduce bias. However, this increased capacity also raises the risk of overfitting, as the model may start capturing noise in the data. On the other hand, simpler models, like linear regression with fewer parameters, are less likely to overfit but may struggle with high bias. The relationship between complexity and model performance is often visualized as a U-shaped curve, where both overly simple and overly complex models perform poorly. The optimal zone lies somewhere in between, where the model is complex enough to capture the relevant patterns but not so complex that it picks up random noise. Adjusting complexity involves techniques like feature selection, regularization, and model pruning, all of which we will explore later. The goal is to find a model structure that minimizes both bias and variance for a specific dataset, ensuring the model generalizes well. Diagnosing whether a model suffers from high bias or high variance is an essential skill for any machine learning practitioner. One of the most straightforward methods to assess this is by evaluating the model's performance on training and validation datasets. If a model performs poorly on both training and test data, it likely has high bias, indicating underfitting. Conversely, if a model performs well on training data but poorly on test data, it suffers from high variance, suggesting overfitting. Learning curves, which plot training and validation error against the number of training instances, are invaluable diagnostic tools. A model with high bias will show both errors converging at a high level, while a model with high variance will demonstrate a wide gap between the training and validation errors. Bias-Variance decomposition can further help in understanding the sources of model error by breaking it down into bias, variance, and irreducible error. Once identified, adjustments can be made. For high bias, consider increasing model complexity or adding features. For high variance, consider simplifying the model, using regularization, or gathering more training data. These techniques equip you with the knowledge to diagnose and adjust your models effectively.
Let's delve into practical examples to solidify our understanding of bias and variance in machine learning models. Consider a real-world dataset like the Boston housing dataset, which includes features related to housing prices. Initially, you might start with a simple linear regression model. Upon evaluating its performance, you notice it's underfitting, indicated by high bias due to its inability to capture the complexity of housing price dynamics. To address this, you might introduce polynomial features, thereby increasing model complexity. As you test this adjusted model, you observe improved performance on training data but notice a drop in test performance, suggesting overfitting, a classic sign of high variance. To counteract this, you could employ regularization techniques like ridge or lasso regression, which add a penalty term to reduce model complexity and manage variance. Iterative testing and tuning based on validation results lead to a balanced model. This practical approach illustrates the iterative nature of model development, where understanding bias-variance dynamics informs decisions and leads to models that better generalize to new, unseen data. Each step provides valuable insights, enhancing your model building expertise. Reducing bias in a model, particularly without inadvertently increasing variance, requires a strategic approach. One effective method is to increase model complexity, such as moving from a linear model to a more complex one like a decision tree or neural network. However, this increase in complexity must be managed carefully to prevent overfitting. Feature engineering plays a crucial role here. By creating new features from existing data, you can provide the model with additional information that helps reduce bias without necessarily increasing variance. Data augmentation, especially in fields like image recognition, is another technique where existing data is slightly altered to create new training instances, helping models learn more robust features. Regularization techniques such as L1 or L2 can also be considered. They add penalties on model parameters to prevent overfitting while allowing for increased complexity. Evaluating the trade-offs of these methods is key, ensuring that the reduction in bias does not lead to a significant increase in variance, thereby maintaining a well-balanced model that generalizes well to new data.
Controlling variance in complex models is crucial to ensure they generalize well to unseen data. One approach is to simplify complex models by reducing the number of features or using dimensionality reduction techniques like PCA. Regularization methods such as L1, lasso, and L2, ridge, are powerful tools to constrain model complexity and thus control variance. These techniques add a penalty to the loss function, discouraging overly complex models. Ensemble methods like bagging, boosting, or stacking combine multiple models to improve performance and reduce variance. Bagging, for instance, involves training multiple instances of the same model on different subsets of the data and averaging their predictions, which reduces variance. Cross-validation, particularly k-fold cross-validation, is another method to ensure that a model's performance is consistent across different data subsets, thereby controlling variance. By systematically evaluating the model on different subsets, you can ensure that it performs well across various data scenarios. Balancing these techniques helps in creating robust models that maintain low variance without compromising their ability to capture the underlying data patterns.
In the realm of machine learning, numerous tools and libraries facilitate the evaluation of bias and variance. scikit-learn is a widely used library in Python that offers various metrics and functions for assessing model performance and diagnosing bias-variance issues. It provides tools for implementing cross-validation, regularization, and even ensemble methods. TensorFlow and Keras, popular for deep learning tasks, offer advanced capabilities for model evaluation and adjustment. For visualizing bias and variance, libraries like Matplotlib or Seaborn are invaluable, allowing you to create learning curves and other diagnostic plots that illustrate the model's performance over time or across different datasets. Automated machine learning platforms like AutoML can streamline the evaluation process by automatically testing various models and hyperparameters for optimal performance. These tools help in systematically evaluating models for bias and variance, ensuring you choose the right model and configuration for your specific problem set. Selecting the appropriate tools and libraries is crucial, as it can significantly impact the ease and effectiveness of your model evaluation and tuning processes.
As we conclude this session on navigating bias variance in machine learning models, it's important to remember the delicate balance between these two essential concepts. Understanding the trade-offs between bias and variance is crucial for developing models that not only perform well on training data but also generalize to new, unseen data. We've discussed key strategies for optimizing model performance, including adjusting model complexity, employing regularization techniques, and utilizing ensemble methods. Practical examples highlighted the iterative nature of model development, where each step offers valuable insights into model behavior. As you continue to explore and apply these concepts, remember that the journey of improving model performance is continuous, with each dataset and problem offering new challenges and learning opportunities. We encourage you to dive deeper into these techniques, experiment with real-world datasets, and refine your skills in creating robust, generalizable models.